Well, our next new topic is called regression. In regression, we're going to be looking at given data points, say a bunch of XY pairs, and we are going to initially assume that they really came from something that for which there's a linear relationship between X and Y. For example, it's known that the surface tension in a fluid is directly proportional to the temperature of the fluid. When the temperature goes up, the tension goes up. It's known to be linear, but maybe we don't know exactly the relationship, the constants of that relationship. If we were to graph the line, what would the y-intercept be and what would the slope be? So we could simply take two measurements of the tension at two different temperatures, and that gives us a line. But there's noise in data. There are errors made, some of them human, some of them mechanical. So we would more likely want to take a large number of estimates at a large number of different temperatures, measure the tension at a whole bunch of different temperatures. And if you plot those, it may not look collinear. They might be staggered a little bit. Well, our goal is to take that data and to make the very best estimate of the slope of the line, the true line, that would show the true relationship between the tension and temperature, and the y-intercept. So we'll get the equation of that line. So, linear regression, and this kind of shows you where we're going, the least squares method. We're given n data points, x1, y1, x2, y2 to xn, yn. And in my example earlier, x1 could be the temperature, and y1 could be the tension in the fluid that had that temperature. And here's what we want to end up with. We want this. We want to know the relationship. We're going to estimate the slope of that line, and we're going to estimate the y-intercept. So how could we do that? Let's say we've got data that looks like this, and we do know or suspect that the relationship between x and y is linear. So I'm just going to make a very rough guess that the line might look like this. Probably a little bit off, but let's just use that for the example. Notice it doesn't go through any of the points. It almost goes through that one. And it's not necessary that it exactly hit any of the points. Now, what we're going to compute is a residual error. How far is that line away from matching our data perfectly? Now, it can't match it perfectly because there's no line that goes through all those points, but we're going to take a vertical distance from each point to our line. Even though we don't know, we can draw it this way, but I don't know what the slope of that line is. And we're going to look at each one of those and figure out how could we get, let me just write this as, let's call this point xi, yi. In my drawing, it's probably x3, y3, but just some arbitrarily chosen point. And we'll call the error that distance, how far it is away from our line. So this point happens to, in my picture, looks like it has the largest error. But every one of those points has a residual error associated with it. So one thing we could do is sum up. Here's what we would do. We want to minimize something. We want to find the slope and y-intercept of this line, so we'll get an equation that looks like this, that minimizes the residual errors. So we could minimize the sum of the EIs, I going from 1 to n. Does that sound reasonable? Well, maybe for 1 second it sounds reasonable. But notice what's going to happen. Based on even on this example I drew, it is possible that that residual error is 0, which would make you think your line is perfect. Because notice, this error, if we took the actual data point minus our predicted value, which would be this, that would be a positive number. All of them above this line would be positive numbers. All of them below the lines would be negative numbers. It's possible they're going to cancel each other out and give you 0, which makes you think you've done something great. But there's an infinite number of lines. You could probably, if you changed it, did the slope downward, you would probably also get, or could get, a 0 sum of the errors. So that's a terrible method. Because, as a simple example, 2 points. One could be exactly 2 above, one could be exactly 2 below. Your error, if you add them up, 2 and -2 is 0. Now tilt that line a little bit, and maybe now you get, 1 and -1, or 10 and -10. So that, I'm going to put a line right through that. That's a bad idea. So how about if we take the absolute values of all of them? Well, you can easily show, just through some examples with a small number of points, you could convince yourself that this will still give you possibly an infinite number of points that have exactly the same residual error. So an infinite number of points that are excellent, and that's we don't want that. We would like to get one line that is the best. So this isn't good either, because we could not compare, we could not sufficiently compare 2 different lines using different A1 and A0, because they could be the same. The residual errors could be the same, so you couldn't really say which line was better than the other. What we are going to use is this. I don't even need the absolute values because we're going to square it. Square the residual errors. This is what we will do. That's what's called the least squares method. So we're going to get one line. When we all compute it, we're all going to get exactly the same line that regresses the given data. So what we're going to have to do to derive something like this is, remember, we don't know the slope of the line. We don't know A0 and A1. So we're going to have to just keep them as variables. And then we're going to have to do some calculus. We're going to have to take some first derivatives and minimize or maximize, setting things equal to 0 and solving, and to find out what A0 and A1 will be the best fit for us. Okay, so I just drew that little thing up there just to make a comment. If that's x, I, y, I, then this distance right here, this would be our predicted value, and that would be x, I, comma, well, our predicted value, remember that y equals a0 plus a1x, this would be a0 plus a1 xi. That's the true value of the data given to us, but for the line that we're going to compute, this point would be our estimate at xi. This would be our estimate, and the height of that line, the value, is going to be this in our estimate, and that's the true value. So you'll see that our residual error is going to be the true yi minus this estimate, which is just the point on the line at xi. Okay, so I wrote our goal, best fit this line to the data, which just means find the best possible value using the least squares method for A0 and for A1. I just defined our residual. Our residual is yi minus our predicted yi. And maybe I'll write this like yi minus A0 minus A1x. And we want to minimize not the sum of these, but the sum of those squared. We're going to square each EI, add them up, and minimize that. So minimizing the sum of the squared residuals, which we're calling S sub R, the squared residuals, well, we know that that is this, the sum I going from 1 to n of the residual errors squared. And this is equal to, I'm just going to do a substitution, this in parentheses squared. Again, that's our observed yi value at the time. If you want to think of x as being time, you can think of it as temperature as well. But at time xi, that's the known value, and this would be subtracting then our estimate on that line. So we need to find out what A1 and A0 and A1 are. So what do? We take, or we find, actually I'll say set. I want to make sure I have enough room here, so I'm going to squeeze it in and write small. Set the partial derivative of SR with respect to A0 equal to 0, and the partial derivative of SR with respect to A1 equal to 0. Remember, A0 and A1 are our only unknowns right now. What will this give us if we take this derivative and set it equal to 0 and this derivative and set it equal to 0? We're going to get two equations with only two unknowns, A0 and A1, and we're going to be able to solve for them. Okay, so I'm going to alternate colors just to make sure the lines don't get blurred together. So, the partial of SR with respect to A0 is equal to, we're just going to do it one at a time. We're going to differentiate one at a time. So I equals 1 to n of what? Well, if we take the derivative of this, we're going to have to bring the 2 down, times yi minus a0 minus a1x. And then we need to multiply times the derivative inside here with respect to a0, which would simply be the negative 1. And underneath that, before solving this or simplifying it, I'm going to write down partial of SR with respect to A1. We're going to do similarly. We're going to take this, 2 comes down, times yi minus a0 minus a1x. Now what do we have to multiply it by? The inside derivative. With respect to a1, if we're taking the derivative with respect to a1, this is actually an xi. What's the derivative of a1 with respect to a1? Negative xi. Remember, the x's, xi's, and the yi's are known to us. Okay, I'm going to call this 1. I'm going to call this one 2. And I'm going to rewrite, I'm simplifying a bit. 1, I'm going to label them on this side. Number 1 gives us, well, think about writing all of this out. This is really a negative 2 here, times all of that. Oops. So we get a negative 2 times the sum of the yi's. That's just taking, that's putting a summation. It'd be like multiplying negative 2 through all of these. And then I'm going to take 3 individual sums, because we know in a summation of of AIs plus BIs is the same as the summation of the AIs plus the summation of the BIs. All right, and then I'm going to get plus 2. These two are now changing to positives because of the negative 2 being multiplied through. A0 plus 2 times the sum of the A1 xi's. And I'm not going to write all of the limits on the summations. They all go from 1 to n. Every one of these summations goes I equals 1 to n. And then number 2, that gives us negative 2 times let's see, now we've got to multiply these three terms through by a negative 2xi. So we're pulling the 2's out in front of the sums, and I'm getting xi, yi for this term. Because remember, this is negative 2xi, yi. There's the xi, yi, and I pulled the negative 2 out in front of the sum. And now we're going to get a sum involving this one. Plus 2 A0xi. And the third one is plus 2 times the sum A1. This time it's going to be xi squared. And I left off the equals 0 in the first equation. So all we did is a little bit of algebra on this equaling 0 here, and on equation number 2 equaling 0 right there. So to save a little bit of room, I am going to just notice that we can, since this is equal to 0 in both cases, we can divide both sides by 2. And dividing the right-hand side by 2 doesn't change the 0. So we just got rid of those 2's as coefficients. Oops. All right, so all the xi's and yi's are known. The only unknowns are A0 and A1. So let's see what we get here. That's an A0. I'm going to reorder these slightly. And what I'm going to do, this is a negative sum of the yi's. I'm going to add that to the right-hand side and keep this on the left-hand side. So equation number 1 now becomes, let's see, the sum of the A0's plus the sum of the A1 xi's is equal to the sum of the yi's. And number 2, doing similarly, gives us that the sum of the A0xi's, this term right here, we're putting this one on the other side. It's negative here, so we're adding it to the other side. Plus this term, plus the sum of the A1 xi's, let's see, that's xi squared, is equal to that, the sum of the xi yi's. Okay, so I'm going to now rewrite them one more time, but simplifying. Remember, I got a little bit lazy here. I didn't write I equals 1 to n on all the summations. But what is this equal to? A0 is just a fixed number. Think of it as being just a constant. And you're adding that number up. 1, 2, you're adding it up n times. That's just n times a naught. Maybe I'll change over to red. So we get, just simplifying these terms, we get NA0 plus A1, and all I'm going to do here is pull the A1 out. It's a constant. You can just pull it out in front of this. So it's going to be A1 times the sum of the xi's. And that's equal to the sum of the yi's. Doing similarly with equation number 2, we're going to pull out the A0 here. Here we're going to pull out the A1. So we get A0 times the sum of the xi's plus A1 times the sum of the xi squareds is equal to the sum of xi yi's. All right, we're almost done. I mean, this is beautiful. We're given the actual data points, x1, y1 to xn, yn. We know what this number is. We know what this number is. We know what this is. We know what this is. And we know what this is. And of course, we know what n is. The only thing unknown is the A0 and A1. And right now we have a system of two equations with exactly two unknowns, a simple setup to solve. I'll even write it like you would not necessarily have to. I'm going to write it like a matrix. Let's take the coefficients of the A0s and A1. So it would be n, and then the sum of the xi's. And then below that, it'd be the sum of the xi's and the sum of the xi squared. Doesn't look like it, but those are our coefficients. This is the A0 column, so the coefficient is n and the sum of the xi's. This is the A1 column, so we've got the sum of the xi's and the sum of the xi squareds, and it's equal to, oops, I have to multiply that by what we're looking for. And over here we get the sum of the yi's, and we get the sum of the xi's. So it may look really bad, but this is really pretty simple stuff. Just remember, we know all the xi's. If we were given the data points, we know what number that is. We know what number, well, that's the same number. And we know what that number is. And we know what this number is, and we know what that number is. Solving, I don't have any room here. Solving, which would take you about 3 minutes to do, just using Gaussian elimination. Solving gives this. A1, the second row, it's a big fraction, so let me use a different color. A1 is equal to n times the sum of the xi's minus the sum of the xi, sum of the yi's, all over n times the sum of the xi squared minus the sum of the xi's in parentheses squared. So you add up all the x values and then square it. Here, you square all of the x values individually and then add them up. And we get A0 equal to the sum of the yi's, over n minus A1 times the sum of the xi's over n. And that's how we get A0 and A1. And A0 could be rewritten because we know this terminology. What is the sum of the yi's divided by the number of yi's? That's just the average of the y's, right? We could call that y bar. Remember, that means the average of all of the y's. Minus a1 x bar. So I'm going to circle a1. A1's the more complicated one, and then I'm going to circle the bottom one because I like looking at it that way better. So to find the y-intercept, all you have to do is average the y's, subtract a1 times the sum of the x's. But that, of course, implies or assumes that you computed a1 first, which is that ugly computation. So that is how you regress data in a linear fashion. Linear regression.